Look at these images. As humans, we can almost instantly recognize that they belong to the same person. But for a computer, each image is only a matrix of pixels. When the angle, lighting, facial expression, or occlusion changes, thousands of pixels change as well. So how can a computer still recognize that this is the same face? Identity is not stored in one single feature like the eyes, nose, or mouth. It comes from the combination of many facial characteristics. A modern face recognition system must learn how to convert a face image into a stable representation of identity. To understand how ArcFace improves this representation, we first need to look at the overall pipeline. A face recognition system usually contains 4 main steps. First, a camera captures a face image. Then, face detection locates the region containing the face and removes unnecessary background information. After that, face alignment adjusts the face based on landmarks such as the eyes, nose, and mouth, so that different images have a more consistent scale and orientation. Once the image is normalized, it is passed into a neural network for feature extraction. The final output is not a person's name, but a numerical vector called an embedding. This embedding is used to compare the current face with known faces. If 2 embeddings are close enough, the system considers them likely to belong to the same identity. Challenges. The goal of face recognition is to create stable embeddings. Images of the same person should be close together, while images of different people should be separated. However, real-world face images contain many variations. The first challenge is intra-class variation. The same person can appear different because of changes in pose, lighting, or hairstyle. If the model is too sensitive to these factors, embeddings of the same person will spread out instead of forming a compact cluster. The second challenge is interclass similarity. Different people may sometimes look very similar. If their embeddings are too close, the system can easily confuse them. The third challenge is open set recognition. In real applications, the system often needs to handle people who were never seen during training. Therefore, the model cannot simply memorize known identities. It must learn a general structure of identity space so that new faces can still be placed meaningfully. Embedding space. To understand embedding space, imagine we have thousands of face photos scattered randomly on a large table. If we organize them manually, we would place photos of the same person close together and separate photos of different people. Over time, each group of photos would represent one identity. Embedding space follows the same idea, but the organization is learned automatically by a neural network. Each face passes through the network and becomes an embedding, which is a point in a high-dimensional space. What matters is not the absolute position of each point, but the geometric relationship between points. The closer 2 embeddings are, the more likely the 2 faces belong to the same identity. At the beginning of training, the embeddings are almost random. During training, if images of the same person are too far apart, or images of different people are too close, the loss function creates an error signal. Through backpropagation, the network updates its weights to pull embeddings of the same identity closer and push different identities farther apart. So face recognition is not simply about memorizing faces. Its core idea is to build a representation space where distance reflects identity similarity. Softmax. To organize embedding space, the neural network needs a clear optimization objective. This objective is defined by the loss function. The loss tells the model how wrong it is, and the network adjusts its weights to reduce that error. Softmax loss is a common choice. After an embedding is produced, Softmax compares it with the identity classes in the training set. Each class has a weight vector that acts like a representative direction. The class that matches the embedding best receives the highest probability. The goal of Softmax is to make the probability of the correct class as high as possible. During training, the embedding space is gradually divided into classification regions. The boundaries between these regions are called decision boundaries. If an embedding lies on the correct side of the boundary, it is classified correctly. The problem is that softmax only focuses on correct classification. It does not directly require embeddings of the same identity to be compact, and it does not force different identities to be separated by a large enough margin. An embedding can still be classified correctly even when it is very close to a decision boundary. But in real-world conditions, a small change in lighting, pose, or image quality can push that embedding into another identity region. That is why face recognition needs a stronger objective, not only to classify correctly, but also to control the geometry of the embedding space. Evolution. For this problem, margin-based loss functions were introduced to make embedding space more discriminative. In 2015, FaceNet used triplet loss based on metric learning. During training, the model compares 3 images: an anchor image, a positive image of the same person, and a negative image of a different person. The network is encouraged to pull the positive image closer to the anchor and push the negative image farther away. This idea is powerful, but selecting effective triplets and keeping training stable can be difficult. Later, researchers found that angular relationships between vectors are very useful for representing identity. SphereFace introduced angular margin into the learning process. CosFace added a margin to cosine similarity. Finally, ArcFace directly added a fixed angular distance, called Additive Angular Margin. The shared idea behind these methods is that effective face recognition is not just about correct classification. It is about creating an embedding space where samples from the same identity form compact clusters and different identities are clearly separated. ArcFace mechanism. For angular margin to work properly, ArcFace begins with normalization. In standard softmax, the classification score can be affected by both the direction and the magnitude of a vector. The model may increase the norm of an embedding to make the prediction more confident, instead of truly learning a better identity direction. ArcFace removes this shortcut by normalizing both the embedding and the class weight vectors to the same length. Once magnitude no longer dominates the score, the model is forced to optimize the angle between vectors. After normalization, all embeddings lie on the surface of a hypersphere. At this point, the position of an embedding is described mainly by its direction. The natural distance between 2 points on a hypersphere is the shortest arc connecting them, and this arc is proportional to the angle between the 2 vectors. This is why ArcFace focuses on angular distance. In normalized softmax, if theta is the angle between the embedding and the weight vector of the correct class, then a smaller theta means a larger cosine value and a higher probability for the correct class. However, softmax only requires the correct class to win over the others. ArcFace makes this condition stricter by replacing cosine theta with cosine theta plus m, where m is the angular margin. By adding this margin, the score of the correct class is intentionally reduced. To still be classified correctly, the embedding must move even closer to the direction of the correct class. Because the vector norms are fixed, the model cannot simply increase magnitude to compensate. The only way to reduce the loss is to reduce the angle theta. Over many training iterations, embeddings of the same identity become more compact around their class center, while different identities become more clearly separated. As a result, ArcFace creates a more stable embedding space and generalizes better to faces that were not seen during training. ArcFace can be summarized in 3 ideas: normalize vectors to remove the effect of magnitude, represent faces on a hypersphere so that angle becomes the main measure of similarity, and add an angular margin to force identities to be more clearly separated. Closing. Now we can return to the original question. How can a computer recognize the same person even when lighting, pose, or expression changes? The answer is that the system does not compare raw pixels directly. Instead, it learns to extract stable identity features and represents them as embeddings in a geometric space. When the embedding space is well organized, different images of the same person remain close together, while different people, even if they look similar, are still separated. The key contribution of ArcFace is not a more complicated network architecture. Its contribution is how it defines a good embedding. An embedding should not only classify correctly, but also reflect clear geometric separation between identities. That is the strength of ArcFace, a small change in the loss function, but a major improvement in how computers understand and represent faces.